Hi everyone, I'm Professor Bergasser, and in this video we're going to be looking at rotational collisions or angular momentum transfer. These are the equivalents of the collisions and momentum transfer problems that we saw earlier in the course, but now transferred over to rotational motion. And we have an equivalent momentum impulse relation for angular momentum. The change in the angular momentum of a system is equal to the net external torques acting on the system times the time frame for the interaction. And if you have a system in which there's no net external torques acting, then that system may exchange angular momentum between its different parts, but of course the net angular momentum of the system is going to stay constant in the absence of any external torques. So we're going to follow a very similar process that we did for looking at collisions and angular momentum transfer for regular linear momentum, and that's looking at the differences between the initial and final momentum, so computing that initial and final momentum across this interaction, as well as the rotational kinetic energies across this interaction, and making sure we can write those down for those two steps, and then looking to see if there's any net torque acting on that system during the interaction. In many cases, the interaction may be so quick or maybe in sort of an isolated environment where there's no net external torques acting. In that case, we can equate the initial and final angular momentum to each other. If not, we can just compute the impulse due to torque. We can also determine the elasticity of the collision. We can either compute ahead of time the kinetic energies and see if it's an elastic, inelastic, or superelastic collision, or we might know that the interaction is one of those three, and you use that to constrain the rotational angular rates of the components of the system we're looking at. And finally, we can then solve for the unknowns in our problem. That might include adding some constraint equations to the motion. And then, of course, we want to make sure we check our solution that it makes sense, we have the right units, and we can check for some extreme values in the expressions that we derive as a result of looking at angular momentum conservation. So as an example, let's take a look at gear mechanisms. Gears which have teeth on them mesh together, and if you've got one spinning, that meshing gear can cause the other gear to spin around at a rate depending on the radii of the different gears. All right, these are very common in clocks, different motor mechanisms. They're also very important for bicycles, in which you have a gear mechanism that's connected through a chain. In any case, we can look at what happens when these gears mesh together and see if there's any angular energy loss as a result of the collision or the interaction between these two spinning elements as they mesh up in their gear teeth. So let's make some assumptions about the structure of this problem. Just to keep things simple, I'm going to assume that the moment of inertia of a gear is about the moment of inertia of a solid disk, right, of mass and of given mass and radius, and that's equal to 1/2 times the mass times the radius squared. All right, that will allow us to compute at least the angular momentum between the two components. All right, and we're starting off with one gear that's rotating at an angular rate omega. It's going to come into contact with an initially stationary gear. And I'm going to assume for this problem that there's no external torques acting on these gears. When they come together, they link up. That's an internal interaction, but there's nothing external to the system that's causing a torque on either of these gears. All right, so that means that when we compute our initial and final angular momentum, the initial angular momentum is entirely contained in the rotational angular momentum of the first wheel. All right, so that's just equal to I, which is 1/2 times the mass times the radius squared, and let's label them separately as mass 1, R1, times its initial rotation rate squared. Sorry, it's not squared, that's actually just regular because it's I times omega for the initial, for the angular momentum. And our final angular momentum is going to be 1/2 times m1 r1 squared times its angular momentum after the collision, plus the second wheel will have its own angular momentum, m2 r2 squared, times its angular momentum after the collision. And just to keep in mind, when we're defining these angular momentum, we're defining them about their centers of mass because we're looking at the angular momentum of the system. I'm assuming that these two objects are not rotating around each other about a common center of mass. We're going to assume that they stay physically in place. That's something we can look into in terms of other mechanisms such as colliding objects that are sort of spinning relative to each other. But we're going to assume for this moment that those objects are not rotating around each other, they're just spinning about their centers of masses. Now, again, because we're assuming there's no net external torques, we can set these two terms equal to each other, and that gives us a relation between our known initial angular momentum, but we've actually got two unknown rotation rates, angular rotation rates, on the right side of our equation with just this one expression. So we can't quite solve this yet. However, we do have a constraint equation we can apply here, and that's the idea that when you have these gears that are meshing up with their teeth, that means that those teeth have to rotate relative to each other at the same rate. And this provides a constraint on essentially how the surfaces mesh together as they come into contact. And specifically what we can say for our constraint equation is that the angular speed of the surface of this wheel is going to be exactly the same as the angular speed of the surface of the other wheel. They're going to lay onto each other at exactly the same rates, which is really what the angular speed is measuring. So the angular speed is, of course, r1 times omega 1, I'm going to say prime because we're looking at the after the collision instance, and that's equal to r2 times omega 2 prime. And that gives us a relation between let's do omega 2 prime is equal to omega 1 prime times the ratio of the radii. Incidentally, this is commonly referred to as the gear ratio equation because it tells us how the gears will rotate at different rates based on their sizes and also gear spacing. So I'm assuming constant gear spacing for this one. It would be different if we're assuming the teeth are actually lined up in different ways. But this is a simple expression for looking at how different gears will rotate at different rates. Okay, so this is our second equation, so that's going to allow us to solve for our unknowns. So let's go ahead and compute then the expression for the rotation rates here, so we can solve out for our final angular acceleration rates. I'm just going to write m1 r1 squared, omega 1 squared, omega 1 just linear. Again, we're still doing angular momentum, so I'm just dropping my half terms here. That's equal to m1 r1 squared times omega 1 prime. And then for omega 2 prime, I'm going to substitute in my expression for the constraint equation here. So that's going to be plus m2 r2 squared times r1 over r2 times omega 1 prime. And we can isolate omega 1 prime by simply combining these two values together and then dividing through. And what we'll find is that this is equal to 1 plus m2 over m1 times r2 over r1 to the minus 1 value. So 1 over that expression in there. Really, that just came from dividing through m1 r1 squared. You'd see this is 1, 1, ratio of masses, ratio of radii. One of those terms cancels out, and that's how we get this expression here. Okay, so this relates the angular rate of the first gear after the collision to its original angular rate. And of course, we also have an expression for what the angular rate of the second gear is after that collision. Now, the question was asking if we lose rotational energy. And to figure that out, let's just take one example where we have mass 1, mass 2 are the same, so two identical gears, so their masses are the same, their radii are the same, and that means that the angular rates after the collision will be the same, and it also means that the angular rate is going to be equal to our initial angular rate times this factor, 1 plus 1, 1, so that's 1/2. So that's equal to half the initial angular rate. All right, so now to figure out if this is an elastic or inelastic collision, we just have to compute the change in kinetic energy. Well, the kinetic energy after the collision is just 1/2 times our I term, which is, again, 1/2 mr squared. I've dropped my 1 and 2 because they're the same mass and radius, times the angular rate, omega 1 over 2 squared, and in fact times 2 because I have two gears that are spinning. Our initial kinetic energy is just 1/2 times 1/2 mr squared times the original angular rate. And when you compute the change in kinetic energy, that's just final minus initial. What we're going to find is that, okay, so we're going to have 1/4, another quarter, but times 2. So we've got 1/8 mr squared omega 1 squared minus 1/4 mr squared omega 1 squared. And this is equal to minus 1/8 mr squared omega 1 squared. And that is less than 0. So we did lose kinetic energy, so this is an inelastic collision. Now, if you think about it, we've actually lost half of the energy as a result of this collision. And if you go back and think about the collisions we've had before in the past, we've got two objects coming together, or one object coming at another object, and they stick together. You typically lose the maximum amount of energy in that case. You typically lose half of the kinetic energy if those masses are the same. And so that is a perfectly elastic collision. And in fact, that's what we see here. This is also a perfectly inelastic collision. And of course, it is that because when these two gears come together, their rotation rates stick together, right? They're rotating at the same rate. So we've lost energy in order to get these to sync up in the same rotation rates, and this is the maximum amount of energy you can lose for this perfectly inelastic case. Now, where does this energy go? Of course, when you're putting gears together, they're knocking each other on the gear teeth. That's going to set up vibrations in the gears themselves. That may produce sound that emanates away from our system, and it's also going to produce heat. And all of these elements are things that we are maybe concerned about if we're building an engine that runs at very high speeds. This may change our design for our gear system in order to reduce some of the energy loss, and we can do that by playing with some of the ratios of the masses and radii of the gears that are operating inside that engine. Now let's look at another example, a case of an elastic collision, but one in which momentum is not conserved. And that's a case of just taking a ball and spinning it and letting it bounce off a surface. You can see that there's a change in motion that even though the ball is falling down straight away, it bounces off to the side. So there's clearly some non-conservation of momentum going on because we've changed momentum in one particular direction in that interaction with the box. Now we can approach this with our same formalism of looking at momentum change, which is the impulse, total impulse acting on the ball. And we can also look if there's any impulse acting in the rotational direction. But if we have the case of an elastic collision, we can also use the energy conservation aspects of this collision to solve for the final motion. Okay, so let's break this down. If you recall, one of the ways of breaking down these kind of collision problems is to look at this problem in different acts, different stages of the motion. So we're going to start this ball from a particular height and let it drop down with some certain amount of spin. It's going to collide with the box or the floor, and then it's going to bounce off in some direction. So the question is, what is that motion after the bounce? So the acts that we have to analyze are as follows. We've got the falling motion, and that we can solve using our regular energy conservation, because this is just interaction with our gravitational potential, which is a conservative force. All right? We're going to have the bounce, which is a collision. And so we're going to use both our momentum impulse, and because it's an elastic collision, we can also look at energy conservation as well, and specifically conservation of kinetic energy, since an elastic collision conserves the kinetic energy. All right, and then we can look at the subsequent motion. That's going to be an acceleration by g, and this is ballistic motion. We've seen this before throughout the class. Pen here. Okay, so the next step is to look at what are the things that we know in this problem and how do we set up our solution for these different acts. We're given a few items in our list. We're told that this is a hollow elastic ball, that it's dropped from a height h and has initial spin rate omega, and it makes a completely elastic bounce. All right, so that gives us a few clues of what the things we're looking for. So our knowns include the moment of inertia of our object, and that's for a sphere, a hollow sphere. And we can either calculate that or look it up, and that's 2/3 mass times the radius of the sphere squared. All right? We're also given an initial y coordinate that's equal to h, and we can assume our initial x coordinate, since that's not given, and we can set our coordinate system any way we want, is equal to 0. Now, I've explicitly decided to set my coordinate system here so that it's set, and actually let's clarify this a little bit. I should set it so it's at the floor here. All right, so let's just erase that. This is a point where it's important to make sure we set our origin as accurately as possible. All right. And while I haven't drawn this way, I'm going to assume that, in fact, this origin is underneath the ball. That way we don't have to worry about any x offset. We'll see x motion after the bounce. All right. Now, we're also told that the initial spin rate is omega, and this is an elastic collision. So that means that the change in kinetic energy translational and the change in kinetic energy rotational is equal to 0 as a result of this collision. So all of these pieces of information we can use to derive our solution. All right, so the approach now is to write down the different the energies as we go through. We're going to go ahead and assume that we can solve this one right away, because that's a problem we've done before. So that will actually give us an initial velocity of the ball when it reaches the surface of minus square root 2gh, right? And that's the initial velocity in the y direction. And you can go back to previous videos to see how we derive that just from conservation of energy. I'm going to focus on this step right here, the bounce, because that's the one which involves some look at the rotational collision aspects of this. And as we've done before, you want to write down the initial and the final quantities of momentum and energy, both in momentum, both in a translational sense and a rotational sense. So let's look at the initial translational momentum, which is p. As we've computed before, the initial velocity based on this drop, we can just from regular energy conservation in a translational sense, is minus 2gh. So we can write this as that's equal to mass times square root 2gh minus in a y hat direction. And the final velocity, since I saw that the motion of this ball goes in different directions, we can't just assume that's going to be in one y-axis. So let's just assume that there's going to be some mvy in the y hat direction plus some mvx in the x hat direction. And I'm putting my prime notation to indicate the velocities after the collision. All right, we can also write down our angular momentum both before and afterwards. The way I've set up this ball, it is spinning in this direction, so using my right-hand rule. We have the case where the direction is pointed back into the board, and so that is away from you. And so we can write down that as a actual vector as the moment of inertia, 2/3 mr squared times omega, times our into the board away from you vector notation. That's our x with a hat around it. Remember, that's looking at the feathers that are going away from you. And we have, let me be careful here about putting my equal sign before we do that. We have our final momentum, and that's just going to be 2/3 times mr squared times some final angular rate, which we haven't decided which way that's rotating yet, and we'll see that's actually something that matters. In both of these cases, we have external forces that are going to be acting on the ball. So as it bounces on the floor, there's a normal force that's experienced from the floor, and that's not a force internal to the system because the table is supported by another table, by the floor, by the earth, et cetera, et cetera. So that's an external force. So we can't set these two things equal to each other, and so we have to keep in mind that we're going to have to compute the impulse done in a momentum sense. Now, as we'll see, that contact also involves some frictional contact, and that means that you're going to also see a torque, as we'll see in a moment. So that's also something we can't assume that the angular momentum is going to be conserved. So this is also not equal. So we're going to, in both these cases, be computing an impulse, both in a translation and a rotational sense, to figure out the difference between these two. Let's continue on and compute the kinetic energies in translation and rotation. All right, for the initial case, that's just 1/2 times mv squared, but in fact, I don't even have to write that because we computed the 1/2 mv squared from the change in the potential energy, and that was just gh. So the total, that's gh is the speed, so the total energy that we get is actually mgh. That's from our initial height, right? So that's the equivalent of 1/2 mv squared at the bottom. Of course, that's where that 1/2 mv squared came from our mgh. All right, and then the final kinetic energies, well, again, we're not sure which way this is going to move, so let's write down those two speeds explicitly, 1/2 mvx squared plus 1/2 mvy squared. And in this case, we were told that this is an elastic collision, so these two terms are going to be equal to each other. And finally, we have our kinetic energy of rotation. We're given an initial kinetic energy of rotation based on the initial speed and our moment of inertia. That's 1/2 I omega squared. If we compute all that out, that 1/2 cancels the 2 and the 2/3, so we'll get 1/3 times mr squared times our initial omega squared. Let me make sure I put that initial there. And our final rotational energy is going to be the same, I, because we haven't changed the object, times the final rotation rate squared. And again, in the absence of any dissipative force that's acting here, and we've told that based on the fact that it's in a completely elastic collision, that's the assumption we're making, then we're going to have these two numbers being equal as well. Now, next thing we can do is calculate expressions for the impulse. Let's do that in a different color. All right, the impulse is going to be happening along many different axes, both the translation and rotation. To get an idea of what an impulse, let's do a quick force diagram, of course, to see what forces are acting on the system. We've got our ball, and this is happening at the contact point with the surface here. Of course, throughout this motion, we're going to have a weight force acting at the center of mass, mg. At the contact with the table, you're going to have the contact forces of the normal force and the friction force. And so, of course, that's going to be pointed off in this direction for the normal force at the contact point. And now we have to decide which way friction is acting, if it's acting. Now, we did see that the ball moved off into one direction, so you need to have a force to accelerate it in that direction and give it some velocities in that direction. And you can imagine as this ball is rotating as it comes to the surface, the bottom surface is going this way relative to the table. And of course, friction force always acts to resist those kind of tangential motions. So the friction force is going to be acting in the opposite direction of the relative surface motion. And of course, that's the direction we saw the ball head off as it bounced off. So that's where the force is going to act. We can now look at this problem and take a perspective of what both the forces and the torques are. For the forces, this is a fairly straightforward calculation. If we want to look at the change in the x momentum, this is just equal to the friction force, Ff, times the delta time, the amount of time it takes for this collision to happen. If we're looking at the change in the y momentum, right, that's going to be the combination of these two forces, which is Fn minus mg times delta t. And we can calculate the change in the angular momentum, and I'm going to explicitly make this a vector so we can make sure we know which way the torque is acting. Of course, that does equal the torque times the time at which it takes place. And now we have to calculate what that torque is. The easiest point to make this measurement, of course, is going to be at the center of mass. And since we're just looking at the collision point, we can choose that for this part of the problem to be our coordinate system, be the center of our coordinate system. So if we draw our coordinate system centered right there, and I'm going to give these prime notations because we're just calculating it at this point, then you can see that, first of all, the weight vector is centered at the origin, so it doesn't have any torque component. The normal force is going to be from the origin down to the contact point is anti-parallel to the normal force, so there's no cross product there. So not surprising, the only thing that's causing a torque is the friction force that's acting along the bottom of the ball here. And again, using our right-hand rule, we can point down, and that's the direction from the origin to where the forces contact, cross our force, and you can see my thumb is pointing out toward you, and so this is going to be the friction force times the radius of the ball times delta t, and the direction is our out of the board vector, toward you vector. That's the point of the arrow coming right at you. Okay, so all of these terms now we can combine to look at, to solve for our unknowns, and we look carefully. What we've got as unknowns is the final speeds in the y and x direction. We have our final rotation speed here, and we actually have quite a few equations to solve these for. So we've got 3 unknowns, and we've actually got a whole string of equations for which to solve this for. Now I should say the other unknowns are also the friction force, the normal force, and this delta time. So we will actually need all of these equations to get at some of these quantities. All right, now that we have all of our equations of motion, let's start to look at them and see if we can solve for our unknowns. We'll start with our rotational quantities, and just a reminder, we have our angular momentum equation where we're looking at the difference between the final momentum, 2/3 mr squared, times the final rotation rate, and I've written this as a vector. That's minus 2/3 times mr squared times our initial rotation rate, which we calculated was going to be pointed away from you into the board. That difference is equal to the torque, which was the friction force times the radius times delta t, so I should be carried the torque impulse. And then we calculate the direction as pointed into the board, okay? And again, that's because we're doing a friction force that's pointing that way, it's pointing into the board. Now, we could change this into the out of the board vector, or away from you, sorry, into the board vector by just flipping the sign, because the into the board is in the opposite direction as the out of the board. So now we have these vector components pointed in the same direction, and I can just simply write down the rotational, final rotational rate in that same direction. So we can turn this basically into a scalar equation. Now before we get to that, let's look at the kinetic energy one, because that was a much simpler expression. That just told us that 1/3 mr squared times the initial rotation rate squared is equal to 1/3 mr squared times the final rotation rate squared. Now you'd be tempted to then say, oh, it must be that the final rate is equal to the initial rate. We have to be careful because remember these are vector quantities. So it's true that we can say that the magnitude of the initial rotation rate vector, and we don't have to say squared because it's going to be the magnitude no matter what, is equal to the magnitude of the final rate vector. But we did see that there was some change in the rotation as there was a contact with the table, and that in fact change in rotation is going to be responsible for the motion as the ball bounces off in a different direction. So there's 2 possibilities for this. Either the rotation rate is unchanged, there's no torque acting on the system. We're pretty sure that's not true because there's a friction force acting over some period of time. The alternate possibility is in fact the rotation rates reverse in direction, because the magnitudes of those 2 vectors are still going to be the same even if they point in a different direction. So for this completely elastic case, which allows us to set this equality, what we can conclude is that the final rotation vector is equal to the magnitude of the initial rotation vector, all right, angular rotation rate vector, but it's pointed in a different direction. It's going to be pointed in the dot hat direction, so even though it's rotating this way as it's coming in, what we're concluding is as it bounces off, it's going to rotate in the opposite direction. So that vector points out towards you. And that's of course equal to minus the rotation rate vector if I just flip that vector around. And that's important for putting all these vectors in the same direction. Okay? So that comes from looking at kinetic energy. And we've seen this before when we've had two equal objects that come in and have an elastic collision. Their velocities will reverse, they'll bounce and go in a different direction, but the magnitudes of the velocities are the same. Same thing with the ball just bouncing straight down. Even though the velocity changes direction, the magnitude of that vector is still the same. That comes from kinetic energy conservation. That comes from the elastic collision. All right, so putting all this in, so now we can set omega f here to be equal minus omega I. And so we get basically two of the identical terms here, minus, both negative. That's equal to negative there. If we write all this down, we can solve for this combination ff r delta t. So that's this term right here. All right, that's going to equal twice these terms. So that's going to be 4/3 times mr squared times omega I. And that's going to be important for solving for that unknown friction force, which is actually a complicated friction force because it's acting as this object is making contact. And because it's an elastic collision, there's no loss in energy. There's no slipping from this friction force. All it does is change the direction of the motion. So it's not one where you can just assume that it's the kinetic energy coefficient times the weight force or the normal force. In fact, it's a much more complicated force. But it's just equal to this expression for the change in angular momentum. Now let's turn to our translational motion. Since we've solved for the rotational motion after the collision, we're going to be looking at our translational quantities. And again, using the change in momentum and the conservation of kinetic energy in the translational sense. Now, we're mostly interested in that motion of the ball that's coming back up and off to the side. Let's look at that side motion, the change in the momentum in the x direction. All right, that is the final momentum in the x direction minus the initial momentum in the x direction. But remember that when we dropped the ball, there was no initial momentum in the x direction. So this is going to give us entirely the momentum in the x direction, and that is going to come from the impulse from the friction force. All right, that is the friction force times the change in time over which that force acts. That's the impulse. Now, we actually have already solved now the combination of friction force and delta t. If I divide this equation by r, I'm going to get 4/3 times mr times the initial rotation rate. And since the only unknown in this equation is really that x direction of velocity, we can go ahead and just write that out as 4/3 times r times omega I. So we've got at least one component of our velocity solved for using that equation. Now I can either turn to the change in the y momentum, or I can look at my conservation of translational kinetic energy. And let's look at the latter, because anytime you have a conservation law, that's really going to provide a lot more insight and easier equations to solve. So the kinetic energy, what we found was that the initial kinetic energy, which came entirely from the drop from a height h, was equal to 1/2 mass times the final x speed squared plus 1/2 times the mass times the final y speed squared. And we have solved for this one as 1/2 mass times 4/3 r omega I squared plus 1/2 times the y speed squared. And we can simplify this a little bit by canceling out our masses. And we can also multiply by 2 on both sides. And what we'll find is if we look at just the vy squared term, well, that's going to equal to 2gh, and then minus this quantity squared, which is 16/9 r squared omega I squared. And this is our initial, this is our y velocity after the collision. Now, let's look at this a little bit carefully here. If I had a ball that was not spinning as it falls down, this is a problem we've seen before, if it has an elastic collision with the table, that means all of the kinetic energy that's coming into that collision is going to manifest itself out of that collision, which means the y speed is going to be the same coming down as it is going up. Just the direction changes. And we've seen this part of the solution before as just a flip of the sign for the velocity as it comes down. Now we've subtracted a little that y speed out, and where did that energy go? Well, it went into the x motion. All right, this is the component that comes out from the x motion of motion. So we just translated the translational energy from one direction and put some of it into another direction. And that transfer has happened through our frictional force. All right? That's provided the sort of change in the energy from one component to the other one. In any case, now we've got a set of quantities. We've got our final speed of angular speed, which is just equal to the initial angular speed. We have our components of x and y velocity. We've actually now got enough to set up our step 3, which is really just ballistic motion. And if you recall, if you have any kind of constant acceleration problem, all you need to know is the initial position, the initial speeds in every component you're looking at this problem, and you can solve for the motion thereafter. Well, we have our initial position at time 0. If I've set my coordinate system so that it's equal to the origin at the point of contact, that's just 0, 0 for that. And we now have our initial speed for part 3, which is just our Vx prime, Vy prime, which is written in terms of quantities that we already know. So with these initial conditions and the fact that our acceleration is just equal to 0 minus g, this is now a 1D constant acceleration motion problem, and we can solve it just the same way that we did in the first couple weeks of class.